let's move to the second section, fluid chemical reaction. As we mentioned before, fluid included the gas phase or the liquid phase. So here can be the gas reacted with liquid or two insoluble liquid reactions. Okay, so let's give you a sample, some examples about the fluid reactions. It can be you produce a desired product, or you want to separate a gas or liquid from a mixture. So for example, like the soap formation, it will be the fatty acid react with the aqueous alkalis. So it can, for example, here is the sodium hydroxide. Then it will generate the sodium source of fatty acid with glycerol. So this belongs to liquid reactions. It's two insoluble liquid. It can be related with the chlorobenzene production, which means you have a liquid benzene react with the chlorine and you will generate the benzene chloride and HCl. So it is a typical gas liquid reactions. Also belongs to fluid reactions. And the second part is probably you want to separate one compound from a mixture. So the example here is you want to remove the carbon dioxide from a liquid mixture. So you are going to use the potassium carbonate to remove the gas carbon dioxide, and you will generate the liquid form. So in this case, you can successfully remove the carbon dioxide from a liquid mixture by adding the potassium carbonate inside this liquid mixture. Then you can do that. Okay, why? Because you are going to generate the liquid, the product in liquid form. So you are going to have, you can remove the carbon dioxide here. So this is also a fluid reactions involve the gas liquid reactions. So no matter which one, in fluid reactions, as we mentioned, you still need to deal with the diffusion part. What this means, so I'm going to give you I'm trying to draw a cartoon to represent what's the fluid reactions. So it can be a gas A react with liquid B, or liquid 1 react with liquid 2, and liquid 1 and liquid 2 belongs to insoluble liquid. So here we focus on the gas A react with liquid B, and we are going to generate product R. In this case, we have gas A here and liquid B here, and in between we call the gas liquid interface. And because this is our two different phases involved, right? So as we mentioned before, as long as you see two different phases, and in between, it will generate a film layer. Film layer actually just tell you that the molecule is going to diffuse through this film layer. Okay, so it's a film layer. And in this film layer, on your left-handed side, close to gas phase, we call it a gas film. And on your right-handed side, which close to the liquid phase, we call it as a liquid film. So next, I'm going to try to draw the concentration of gas A or you can call it a partial pressure of gas A as a function of location, to describe how the molecular A or gas A penetrates through these different layers. So the partial pressure of gas A will remain constant in gas phase. When gas A tries to enter the film layer, the concentration or the partial pressure will decrease as a function of location. But when gas A tries to enter the liquid phase here, you need to consider probably there's a solubility problems here. So based on the Henry's these equations, which imply that the partial pressure of the react gas A will be equals to Henry's constant times the concentration of reactant A. So based on this equation, we know as long as you have a partial pressure here and you divide it by the Henry's constant, then you can know the solubility of gas A inside this liquid phase. So this we got the solubility of gas A. And then the molecular A will also, the concentration of molecular A will decrease as a function of time through liquid film. And when it reaches the bulk liquid, this region, then it will remain constant. The concentration will remain constant due to the transport is very fast. No transport resistance here. Okay, so now you have the roughly picture about the concentration or partial pressure of reactant A as a function, how this molecular A pass through different layers. But the purpose here in these sections also want to answer how fast these reactions is. So we want to calculate or estimate the consumption rate of reactant A in, this is 4 prong, so it's in total reaction volume. In order to get this one, so we want to show you how to derive these equations, right? And roughly based on these equations we show here, this can be considered as a driving force. So it will be the driving force. So it will be the PA, partial pressure of reactant A, and finally the A will totally or completely consumed by reactant B. So concentration will drop to 0. So this is serving a driving force. And the bottom part actually is corresponding to resistance. And of individual layers. Okay, so when molecular A pass the gas film, we can have a resistance of gas film, then then diffuse through liquid film. So we have a resistance to describe the liquid film. In bulk liquid, probably it is a reaction. So we also have a resistance for these chemical reactions. So all these reactions belongs to series reactions. So you have resistance 1 plus resistance 2 and resistance 3, and summary that is a total resistance for these reactions. Okay, so if you want to check the details, you can check the figure 23.1 in your textbook. Okay, and the textbook actually is the one we mentioned in syllabus. Okay, so next, in order to show you how we can get these equations to describe how fast or how slow this heterogeneous chemical equation is, so before that we need to identify some new terms here or highlight some important part here. Would be when we talk about the fluid reactions, you need to pay attention about the mass transport rate, chemical reaction rate, and equilibrium solubility. This is quite important because we haven't discussed this in a previous case, right? Because when the gas dissolve in the liquid, they for sure that has a solubility problems, okay? So you need to pay attention for this one. And also the contacting patterns of the bioreactors or of your reactors. All these 4 parameters we need to consider for fluid reactions. So the example people always mention would be something like this. When I have a reactant gas A and it try to bubbling through the liquid B, so it is a gas A react with liquid B. So when you try to answer what's the consumption rate or what's the rate equation corresponding to this gas liquid reactions, so we need to make an important assumptions. Here is we assume these equations belongs to second order reactions. The second order reactions tell you that the consumption rate of reactant A equals to KCACB because 1 plus 1 is a second order reactions. And as we mentioned before, the reactants is gas. So you need to, when gas A in liquid B, you need to understand the solubility. They have a solubility issues in between the partial pressure and concentration of reactant A. And in between will be the Henry's constant. Okay? And I want to highlight the gas A, how the gas A react with liquid B. Try to enlarge this region, and we have gas A and liquid B. And as we know, in between is a film layer. So gas A will diffuse through this gas film and arrive at the interface between the gas and the liquid. And it will dissolve based on the Henry's constant. We can get the concentration of reactant A in liquid phase. And then the molecular A will diffuse through this liquid film layer and arrive the bulk liquid. Okay, so here you need to pay attention for the other assumptions is B, liquid B cannot enter into the gas phase. So gas phase is this region, right? So B, molecular B is not going to enter the gas phase. That tell you what? That tell you very important information that the reaction, these chemical reactions, heterogeneous chemical reactions, either happen in the, for sure is always happen in the liquid phase. So no reactions happen in the gas phase. All reactions happen in the liquid phase, but it can be in the liquid film or bulk liquid or both. So you need to highlight this part is the reaction location can be in the liquid film or bulk liquid or starting or both. That means the reactions happens from the liquid film until the bulk liquid. Some people probably will have some questions. Why or in what kind of conditions chemical reaction will happen in film layer? So you can expect it that if this is molecular A, this laser pointer highlight this is molecular A. When A meet B at the interface, then I believe the transport or diffusion of molecular A and chemical reaction with molecular B will happen together. But which one is faster? Is diffusion is faster or reaction is faster? Let's make assumptions. If diffusion just spend that only takes 1 second, but reaction take 100 seconds, which means the transport is very fast, and reaction when transport just 1 second here. So the molecule after 1 second, the molecule A already moved to here, passing and enter the bulk liquid. But the reaction, as I mentioned, it takes 100 seconds, right? So reaction haven't finished. So in this case, all the reaction will happen in bulk liquid because transport is too fast. But on the other hand, if the transport is going to take transport through this film layer will take like 100 seconds, and reactions just 1 second. So when after 1 second, then reaction already finished. That means we generate product R, but so and also the transport just take 100 seconds, right? So you still transport just move slightly. So this molecular A already generate product R and everything already finished in thin layer. So in these conditions, the reactions only finish or only happen in the film layer, right? So this is why we need to discuss why in what kind of conditions the reaction sometimes probably is in film layer, or sometimes it's in bulk liquid, or starting from film layer to the bulk liquid. What depending on how fast of the mass transport, or how fast of these reactions. Okay, you need to like the difference rate, reaction rate, and the transport rate will determine the reaction locations of these fluid chemical reactions. Okay, so the detail we are going to introduce to you in following slide, just to give you a roughly idea. And next will be, because this is a fluid reactions, so when we try to describe how fast or how slow it is, usually people will use the unit, we call it as the reaction volume. So it will be the consumption rate of reactant A per reaction volume. So and here we use the 4 prong to represent the reaction volume. So what's the reaction volume? Is the summation of liquid volume and also the gas volume in this case. So will be considered this is a reaction volume including the gas and also the liquid. And from previous slide, some people also we use the double prong to represent the consumption rate of reactants per interfacial area, and this is double prong. And in this case, the one we learned in lecture 6 will be consumption rate of reactant A per liquid volume. Everything will happen in the liquid, so we use divided by the liquid volume. So if you want to link these two consumption rate with different units, we can use dA, consumption rate of reactant A equals to R4 prong VR, RAL times VL, and RA double prong times S. We got this relationship, and we divided by VR, so we got the R4 prong equals to FL RAL and equals to ARA double prong. So here is VL divided by VR, VL divided by VR will be FL. And here A actually is the RA double prong. Will be the S divided by VR, so it's A here. So this is just some definitions. Okay, so the most important part is the relationship between these these 3 different consumption rate, okay, with different units. What's the relationship between them? So next, we are going to spend like 2 slides to demonstrate how we can get this relationship, this rate equation to describe the fluid heterogeneous chemical reaction. So the idea will be like that. I will show you. We separate things into 2 parts. The first part we call that we don't have no chemical reactions, only mass transport issues of the reactants. So means the reactant A is going to diffuse through the gas film, liquid film, and arrive back liquid, and no chemical reactions in liquid film, just mass transport of the reactant A. And the second part would be when mass transport is very fast. Fast means the concentration or partial pressure of reactant A remain constant through the film layer, and the reaction only happen in bulk liquid in this case. So we are going to combine these 2 results and to get this rate equation for heterogeneous chemical reaction. And we want to highlight and discuss these results. So let's move to back here. So the first part is we only consider there's no chemical reaction happen in the liquid film. As we mentioned, this is B, right? Molecular B. So when A enter the liquid phase, then there's no chemical reaction happens, only mass transport. So based on this idea, we hope you can try to formulate the rate equation for or consumption rate of reactant A in this case. So how to do that? So usually we will do that like you try to first of all you need to draw these figures. We have partial pressure of reactant A remain constant in gas phase, and when it enter the gas film, the concentration or partial pressure will slightly decrease. And when it arrive the liquid phase, based on this Henry's law, we can get the solubility of reactant A in liquid phase. And then the concentration of reactant A will decrease as a function of location, and when it reach bulk liquid, it will remain constant. So based on this figure, we can write down the flux in the gas film and also the flux passing the liquid film, and as soon they reach steady state, then we have chance to get some relationship to formulate the consumption rate of reactant A, right? So in the gas film, based on the slide you learned from like section 1 would be the flux, the consumption rate of reactant A, or JA is a flux, right? Double prime is a flux. Transport coefficient KAG times PA minus PAI. Okay, and KAG actually is the diffusivity divided by the thickness of the film layer. And the liquid phase, liquid film, the same, right? The flux, transport coefficient KAL, and CAI minus CA. So you have these 2 equations, right? But this is the unit here is by the interfacial area. But as we mentioned before, in fluid reactions, the unit should be per reaction volume should be 4 prong, right? So how to convert? You have this one, and we want to express in 4 prong. So you times the A together. So we will get these results times A, so we got the 4 prong, and this is A. And the same idea, you got the 4 prong times A. Okay, so focus on these 2 equations. When it reaches steady state, means the flux consumption rate will remain constant, right? So steady state, so you can get these two results. And in order to formulate the consumption rate of reactant A per reaction volume, the unmeasurable parameter will be the CAI, is the concentration of reactant A at interface between the gas and liquid phase. It is unmeasurable, so we use these equations. We got this one, right? We use these equations and plus these equations times HA. So we can delete this CAI, then we can get these results. This is a consumption rate of reactant A per reaction volume, expressed like this. And if you look this carefully, it is quite familiar, right? This term actually can be considered as a driving force for these reactions. So the driving force will be concentration, right? So here is a gas, in the unit will be partial pressure. So we will use a PA. And here is not, probably is not equal, CA probably is not equals to 0, so we'll put a CA here. PA, you cannot use PA to the minus the CA, right? Because the unit will be different. So we times the HA, so PA minus HACA serving a driving force. And the resistance, the molecular A is passing through the gas film and liquid film. So as we learned from first sections, the resistance of gas film will be reciprocal of KAG, right? The transport coefficient in gas film, so it will be transport coefficient of reactant A in gas film, reciprocal of transport coefficient. And here, because this is 4 prong, so we have the A here compared to the one we learned in first sections. Okay, in that case, actually the unit is concentration, so you didn't here. So the unit is concentration, so you just use the reciprocal of transport coefficient here. Okay, let's back to the one we just mentioned. And this is the transport resistance in liquid film. And transport coefficient in liquid film here is also reciprocal of KAL and times the A due to the consumption rate here. The unit is per reaction volume. And here we still have HA. Why? Because the bottom part here, the upper portion here is in partial pressure. This is partial pressure O, right? Because we talk about the gas film, so the unit is partial pressure. But here, the unit here is concentration, reciprocal of transport coefficient. The unit here we talk about is concentration. So you need to times the HA to become the partial pressure. Will be consistent with the upper portion. So you have this modified term. But in this case, for heterogeneous fluid chemical reactions, transport coefficient, transport resistance in gas film expressed like this, and in liquid film can express like this, and this will be serving a driving force. So this is for the first part, straight mass transport of reactants. Then next is, this is transport, right? And the A, when A enter the bulk liquid, probably it will react with the B. So in this case, we will say fast transport, and all the reactions happen in bulk liquid. So can you formulate the consumption rate of reactant A will be the 4 prong. So based on these results, we know, and also the rate equation, this is a second order chemical equations, right? So you can write down the minor consumption of reactant A in liquid volume can express like KCACB. This is the assumption we assume. This is the second order reactions. Now you know this one, right? So you directly times the FL, you can get the 4 prong. If you don't remember these equations, you can derive that right away here. consumption of reactant A per reaction volume will be 4 prong. Consumption rate of reactant A per liquid volume will be RAL. You just use list times list equals to list times list, then you can get these results identical with the one I just show here. Or back to here, you already know the list value, you just times FL, you can get 4 prong. So 4 prong, and I put substitute RAL as a KCA/CB, so I get these results. And I want to arrange this by the driving force and the resistance part. So the driving force here, I will assume this is reaction, so the reactant A probably will be totally consumed or completely consumed by inside the bulk liquid. So the driving force here, I will use the PA. Also consistent with here, we use the PA, partial pressure, as a unit. And I put the rest of parts in the bottom, and the form will be similar with what you learn, will be considered as a reaction resistance. And this is a partial pressure, okay? So it's easy to remember. So when you try to combine the two results, I have a transport resistance 1, 2 in gas feed, liquid feed, and also reactions. So I can directly get these results. This is a driving force partial pressure of reactant A and transport resistance in gas feed, liquid feed, and also this is a reaction resistance. So this is in the beginning how the textbook tell you how to derive a rate equation for heterogeneous reactions. It can starting from the simple assumptions, combine two results, then you can get these reactions, these rate equations for this heterogeneous chemical reaction. But however, in this two simple case, we have a bug here. We assume transport reaction, right? But how about if the one is like I mentioned before? How about if if the reaction is very fast, which means when A enter the B and they generate product immediately. That means reactions happens very fast compared to mass transport. Then all reaction probably will happen in the liquid film. But under this situation, we cannot use these solutions to estimate what's the consumption rate of these heterogeneous reactions. Why? Because how we get this one, we assume it is transport reactions. We haven't have chance to deal with the reactions happen in liquid film, right? So in this case, I will ask, if the reaction happen in liquid film, which means that if the chemical reactions is very fast compared to mass transport of reactant A in liquid film, what's the consumption of reactant A? How to estimate the consumption of reactant A? Have any idea? So as long as there's a chemical reaction happen in liquid film, which imply that the transport resistance in liquid film is not only the resistance of liquid film is not only transport, right? You need to consider the reaction part. So here tell you that you need to modify the resistance of liquid film. And how to modify that? Here he introduced a parameter we call E, which is the liquid film enhancement factor. In this case, as long as you put E here, which is liquid film enhancement factor, you are going to modify the resistance of liquid film to allow we can deal with if there's a chemical reaction happen in the liquid film. So what's the definition for liquid film enhancement factor? We will talk about in next slide. But before that, I also want to highlight one important parameter or indicators, which we call a Hantar modulus. What's the Hantar modulus? Based on the definition here, Hantar modulus is a square root of reaction rate versus the mass transport rate in the liquid film. So in this case, just tell you, in this liquid film, reaction is faster or diffusion is faster, or they both are compatible. Right. So this is quite important because it can tell you that whether where is the chemical where the chemical reaction happens is in the liquid film, bulk liquid, or both. Okay, so we have two important indicators to describe the behavior in liquid film. So let's move to the liquid film enhancement factor, which you need to the modified parameter indicators input in this resistance of the liquid film. So here, this is the final rate equations, including the driving force of reactant A and resistance for each layer, which is gas film, liquid film, and also bulk liquid. And regarding to the E, liquid film enhancement factor, what's the definition for this E? Is the rate of take up of A when reaction happens. So the consumption rate of A when we have a reaction happens in this liquid film. And the bottom will be the consumption rate of reactant A when we only have mass transport in liquid film. So as you expected, if you have a reactions, you will consume more A molecules, right? So the E must larger than 1. So the detail is like this. I just enlarge the liquid film here. And this is the mass transport. And as you know, we assume the concentration of reactant A at two ends of this layer remain constant. So we fix the concentration gradient. And as long as you fix the concentration gradient, the flux will remain constant for mass transport, right? So if there's additional chemical reactions, means A is going to react with B, that will consume this reaction, chemical reaction will consume more extra molecular A. That will result the total flux increase, right? Because it needs to consume more molecular A. So based on this idea, we know the E, when we don't have the reaction happens only mass transport, so the E will be equals to 1. But however, if there's some reactions, means A react with B happens, it will going to have more A, consume more A here, so the E must larger than 1 in liquid film. So as you expected, if E, we have more, E is much larger, we have a larger E, which implies there's more chemical reactions happen in liquid film. Okay, so when E is larger than 1, which implies that there's some chemical reactions happen in liquid film layer, it is going to consume more A to passing through this liquid film, right? So more A means the flux will increase, right? So if flux increase, the resistance is going to decrease. But E, when E is larger, means the resistance is going to decrease so you will get more flux. So everything turns reasonable. Okay? So this definition for E or indicator or modification term of E is reasonable because as the reactions happens, you can get larger E. Larger E will result the resistance gets smaller, and that will lead to more flux. So you got the more A passing through this or enter the liquid film layer. Okay? And some people probably will ask, yes, the value of E has a bottom line is equals to 1, and how about if the E have an upper limit, which means that do we have a highest E in the liquid film? Do we have? Yes, we have, because these reactions, when reactions the reactions happens very fast, that will consume more A per second, right? So as long as this reaction reach instantaneous reaction, means the reaction rate is very, very fast, then you will have the maximum value of E, we call it EI. Okay? So next I'm going to show you more, hope you can have more pictures about the fluid-fluid heterogeneous chemical reactions based on different MH, and also we have different MH, means the reaction rate compared to mass transport will be from very fast to slow, and it will affect the reaction locations, and also will lead to different consumption rate of reactant A for these fluid-fluid reactions. So this is we have 1, 2, 3. We have 1, 2, 3, 4, 5, 6, 7. We have 7 different patterns for fluid-fluid reactions. So what's here? We have based on different reaction rate from fast to slow. Compared to mass transport, we have very fast instantaneous chemical reactions, and slower will be the fast chemical reactions, intermediate reactions, and very slow reactions. And the left column, we have the low concentration of reactant B. And this column, we have a high concentration of reactant B. So we have a low concentration and different reaction rate compared to mass transport. Okay, so let's explain each one to you. I want to spend some time from the bottom for the slow reactions. Okay, so probably we can from the instantaneous one, and to slow is the one. Okay, so compared to mass transport, if we have instantaneous chemical reaction, means molecular A meet with molecular B will generate product immediately. So we call it instantaneous reactions. So based on this, if you try to draw these figures, you probably will say gas A will remain constant in gas phase, and when it passing through the gas film, the concentration or partial pressure will decrease as a function of time. And when A enter the liquid film, and this Ca will involve, it will related with the solubility of reactant A in liquid phase, right? But when A enter the liquid film, it will decrease, right? And when A meet the B, they will generate product. So because A meet B, they will react immediately. So we have a reaction plan here. And some people probably would ask concern about the partial pressure A will be here, it will be lower than CA. Actually, the unit will be different. The SS here, sorry, let me draw. The SS here is in pressure, and the SS here will be in concentration. Okay, so different units. So for the y-axis. Okay, so now this is instantaneous chemical reaction, means the A met with B, they will generate product immediately. It's very fast compared to mass transport. Reaction is very fast, so you can get the reaction plan. But you can imagine if the reaction is a little bit slower, which we call a fast reaction. It's not as fast as instantaneous reaction, it's a little bit slower. Then reaction plane will become the reaction zone. That implies that when A enter the liquid film, and yes, they meet B, but the reaction is not as fast as this one, so the reaction location can become a zone. And but all the molecular A will consume completely in liquid film. So you can see the concentration of reactant A will drop to 0. But you can imagine if the chemical reactions get slower, getting slower, then the reaction will include the film layer and bulk liquid. So reaction can starting from here, continue into the bulk liquid. So these two, instantaneous reaction and faster reactions, the reaction only happen in film layer. And when the reactions is slower, getting slower and slower to intermediate chemical reactions, then the reaction location will include the film layer and bulk liquid. And you can imagine if the reactions get slower and slower than intermediate chemical reactions, it will become a slow chemical reactions. Compared to transport, a slow reaction means the transport is very fast. So mass transport is much larger than reactions, faster than reactions. So under this situation, E will be equals to 1, which means all chemical reactions happen in bulk liquid. Transport is very fast. It's the one we just show here. This is the one. Transport is very fast and all reactions happen in bulk liquid. Okay? This is the one you're familiar with in lecture 6, right? When in lecture 6 we talk about the same phase. So when you add the liquid A and in liquid B together, you don't consider the film layer because you consider the mixture process or transport process is very fast. It's the same idea. Mass transport is very fast, so you never consider the diffusion time or how much time is spent in mass transport part. Okay, so everything we consider is how fast this reaction is. So this slow reaction is the same concept you learn in lecture 6. But for heterogeneous chemical reaction, when the chemical reaction slow down to slow reaction, also it is implying that the transport is very fast. And all chemical reactions happen in bulk liquid, so E equals to 1. Because in film layer, there's no chemical reactions. When no chemical reactions, so E equals to 1. Okay? So we ended here. And by the way, as I mentioned, the case I just mentioned in previous slide, if the transport takes like a transport through the film layer, the liquid film layer will spend like 1 second, and the reaction will spend 100 seconds. So in this case, transport is very fast, right? So transport is very fast, and A and B will completely react in bulk liquid, so it will belong to slow reactions. But if the case, if the transport takes like 100 seconds passing through the liquid film and reaction is 1 second, is instantaneous reactions, and you can expect the A will spend 100 seconds to passing the liquid film. But reaction only takes 1 second. So you can image in this case, all chemical reaction will finish in the liquid film layer. Okay? So this can give you more image to have some idea about the difference between instantaneous, fast, intermediate, and slow reactions. Okay? Okay, so today we ended here.